Hello everyone, my name is Eric Nijveld, co-founder of technologycatalog.com. Today's webinar is about an exciting enhanced oil recovery technology. The presenters are Kevin Blackman and John Benton from Hydroacoustics Incorporated, or High Technologies. Kevin is the president of the company and John is the chief development officer. Kevin and John will first deliver a brief presentation, and from there we go to a Q&A session. If you have any questions, you can type them in the Q&A box on the left-hand side. The webinar will last about 30 minutes. It will be recorded, and you will receive a link following the webinar. Feel free to share the link with your colleagues. I would now like to hand over to Kevin. Over to you, Kevin.
So I'm Kevin Blackman. I'm the president of HAI Technologies. We are the parent company of Hydroacoustics, which is the developer of the oil recovery tool that you'll see in the presentation a little bit. A little background on the company. We are a 50-year-old company, primarily doing research and development in the field of acoustics generally, and with a specialty in low-frequency sound and its deployment in very difficult environments. So our client for the last 3 decades has been the U.S. Department of Defense in terms of producing acoustic devices for them in a variety of environments. And our devices are currently used for both communications, for mapping, and then our low-frequency sound technology that we've been developing for the last decade in the oil space uses that to enhance oil recovery. And as John will get into in a little bit, we have been downhole in the Permian basin for the last 18 months, and that's the results of that proof of concept that John's going to talk about today.
All right, thank you, Kevin. My name is John Benton. As Eric mentioned, I'm the Chief Development Officer. So Hydroacoustics, or Hydroacoustics Technologies, or HAI Technologies, is the parent company of Hydroacoustics, which was formed about 50 years ago for work on low-frequency sound at Harvard University, which was then sold, the technology was sold to General Dynamics. So we have over 50 years of experience in low-frequency sound generation. We provide practical and commercial uses for acoustic technology for both the Defense Department and private industry. We have devices in all the Navy submarines at this point and have had for the last 40 plus years. 50 US and foreign patents. Have worked on all of that to get us to the point of taking that technology, the background in acoustic technology, to create the oil recovery tool, which is a robust and reliable device for improving oil recovery at a relatively low cost for the oil and gas industry, and works very well in mature fields. So the principles behind that is based on the use of low frequency, very low frequency acoustic waves for developing pulsed pressure waves through the reservoir. The reference here is a couple of papers. The Pride Geophysics paper talks about some of the details behind it and the theory behind it. The SPE paper that was presented in 2007 clearly talks about the differentiation between ultrasonic and low frequency sound. And ultrasonics is not what we do. We oftentimes get confused with that, but it's the low frequency sound, which is works to stimulate in the reservoir at great distances from the well in which we install it. And what we want to make sure we also clarify is we're talking about the results that we show today as a single installation in a field that's affected an area about within a 2-mile diameter circle. So that would be slightly over 3 kilometers in diameter. The design is patented. When we get through with this, I'll briefly show you. I have one of the devices actually sitting here behind me, so when I finish sharing the screen, I can point that out to you. So you can basically, looking at it, it's about 1 meter long. It fits, fits inside, and I apologize, I can't do the conversion in my head quite quickly. It's about a 3.75-inch diameter device, so it goes inside a small casing. It is scalable, so that we can scale it up to size. For example, say you were going to run one of these in a well in the Middle East, in which you had 7-inch casing, you can simply build these devices to a larger size. We have not built one, but we've done all the work as far as the design work. So we would be roughly, if we were to run something in the Middle East in a well, we would be about a year away from being able to put something into the field for that. What does it do? This is, I mean, you can read what's on the slide. It adds a lot of things as far as increasing oil recovery, which of course adds to your oil recoverable reserves, extends the field life of mature fields. We definitely have been able to improve the injection rate into the injection wells where we run it. In Texas, it's almost it's a 300% plus improvement in the injection rate into the well in which we ran it. And one of the things that we notice is that as we look at this is the greenhouse gas intensity is much less than sort of current popular methods for increasing production worldwide, which is 13 times less than drilling and about 4.5 times from just the leakage and transportation of CO2 for CO2 EOR. So material, when you look at it on an aggregate basis, we would be able to reduce the aggregate greenhouse gas intensity for any operator by running our device. Very widely applicable. It certainly works well for, there's a lot of things that you really wouldn't necessarily get from either workovers or recompletions. Either any one of those, typically workovers will give you not a long-term production increase, just rate acceleration. Doesn't add reserves where recompletions will. If you do have access to a different zone where you can recomplete into a new zone, where we're acting on the existing oil. So the old saying about oil is found where you found it before. That's what we're doing, is we're working on the existing reservoir to increase the recovery over and above what you currently are able to get out of the field. This is a slide that shows what's happened in Texas since we ran this thing in the Permian Basin. About May of last year is when it went full operations, 24/7 operation. As you can see, there's roughly a 30 to 35% continuous and measurable increase in production. And that is after the operator returned a number of wells to production. So prior to running our device, they were only operating about 20 wells within that 3 kilometer circle. Once we started to see a response, the operator then brought the other wells back on. So the sort of the purple middle line that you see in there is what the decline curve for the field was for all 30 odd wells running. And you can see what the differentiation is between that and what it was historically from the result of running the oil recovery tool. And not only have we increased production, we've also flattened the decline slightly. It was averaging, the field average decline was somewhere around the 14-15%. We're now on the 9.5 to 10% decline. So we're going to get a good solid long-term increase in production and reserves adds from this field. The next slide discusses what we've done with the injectivity in the well. Before we ran the device, it was running about 0.3 barrels per day per PSI. We're now upwards of 0.8 barrels per day per PSI. So a significant increase in injectivity in the injection well. And that ties back to what you think you're doing, because what you're doing is you mobilize oil away from your injection well. You increase the relative permeability to water around that well. So it just follows that you're going to be able to increase the injection rate.
And then this last slide, just we're working actively with Pickering Energy Partners in Houston in terms of commercializing the device, and we're happy to make this presentation available to anybody that sends us a note, and we'll send you the presentation. That's no problem.
All right, let me see if I can stop sharing here.
Thanks very much, John and Kevin, for the overview. Very impressive. I see various questions already coming in from the audience. Let me start with a couple of questions that I have here. So can you say a bit how long there has been research into the use of low-frequency acoustics to improve recovery?
So when you think about the research about it, the anecdotal information started, and I'll briefly rate. So here's the device that we were talking about. This is the center section here with the rotary valve in it. This is, like I said, it's about 1 meter long. It weighs a bit under 15 kilograms. So fairly, not really large, pretty easy to run. Back to your question, Eric. Since the 1950s, companies have noticed that they saw increases in production from earthquakes. And so anecdotally, earthquakes create low frequency pressure pulses. And so they saw increased production. I have friends that have shallow fields in the middle of where a railway runs through, and when the freight trains go through, they could see some changes in production. So people noticed that this was something that did act on a reservoir. There were research papers that started in the 1990s. So a lot of the research was done in the 1990s. There were other devices that have been built that went along with this in the mid 2000s. And that's about the time that Hydroacoustics started their work with our first patent in about 2009, first field tests in 2018. So that's a little background on what's been going on with the research there.
Excellent. And are you unique in this, or are other companies doing something similar?
There are some other companies that are out there. A lot of people are familiar with applied seismic research. I think what makes us unique is because of our background in building things that have to last a long time, that we've built a device that's simple and lasts a long time. It's very reliable. The applied seismic research device did demonstrate improved production, but it wasn't very reliable. It was based on where ours is downhole, has just a couple of moving parts in it. The ASR device had to rely on a pump jack and rod pumps to run. So you had a lot of more complexity, and it wore out, and it was an expensive thing to run and replace. We figure our cycle time on this, as far as refurbishment, is about once every 2 years. It's similar to replacing an electric submersible pump. You just go out, it takes maybe a day to swap it out with a rebuilt device and run it back in a hole. So again, fairly simple operation. Installation time, again, takes about a day to 2 days, depending on well depth and some of the current complexity of the well. But everything is off-the-shelf technology to run this thing in a well.
Okay, excellent. And can you say something about the current operational parameters?
So it's fairly broad-based. I mean, we're currently, some of the key things that we're limited to at this point is our static pressure limit, which is about 3,500 psi. So that would be your bottom hole pressure, your active bottom hole pressure. That would be one thing that would be the current limitations on it. We've got a self-imposed gas-liquid ratio limit of about 2,000 standard cubic feet per barrel. Our concern is that over that, if you've got a significant gas saturation in the reservoir, you're going to run into problems with attenuation of your signal. Because the reason why pulse pressure waves work in the reservoir is because you want to work on incompressible fluids for the most part. And the gas saturation in the reservoir is compressible, and so that would attenuate your signal. So that's sort of the two critical ones. We've run it in both carbonate and clastic reservoirs. It's worked well for that. Secondary operations, tertiary operations, we'll run it in primary fields and producers. It's as long as we don't have a high gas saturation. So we've done that, and those were done in upstate New York in 2018, and again demonstrated pretty solid results. We do look at our ideal conditions or porosities in the 12% range or greater, 35% or less recovery factor, about a millidarcy in permeability or better, of course. We would look at running it in horizontal fields and shale fields, but that would be something that's sort of you're testing the envelope at that point. We have looked at that and talked to a couple of different companies about that possibility. Fairly heterogeneous reservoir, Dijkstra-Parsons coefficient of about 0.3. Certainly look at something with bad, not bad, but poor mobility ratios. Continuous reservoirs. That's one of the things you want to look at, is because you're propagating a pressure wave through there. You want to have a sort of a range of that, I think on a hectare basis, about 260 to 300 hectare mappable pay intervals to do that. And there's a couple other things there. There's a pumping rate through the well that you need about 100 cubic meters a day to be able to pump through a device, because the device itself doesn't cost much to run, but because most of the energy is supplied by the water that you pump through it. So that covers most of it.
Hey, excellent. So you covered quite a bit, and actually there are various questions from the audience related to some of the specifics and to assess applicability. Let me go through some of them. One question: what's the diameter, the outer diameter of the tool? Can you say something about that, the diameter? And did you run it with tubing pulled?
Yes, we run it with tubing. I'm sorry, I should have mentioned that at the start. We run it on the end of tubing. So it's just run on standard production tubing, and it's adaptable to most any size. So it's run very much like running an electric submersible pump. We do have a specialty packer. We work with a company to build a specialty packer that allows us to run the power cable through the packer and down to the device, which is hung below the packer. Because in most cases, in injection wells, you have to have an injection packer to isolate your annular space. So it's, like I said, it's a pretty simple process to run it, and off-the-shelf technologies to make it work. And it's nice to be able to run on tubing. Go ahead, sorry.
Sorry, as John said before, the diameter of the tool that sits behind John is 3 3/4 inches and currently goes down a 4.5-inch casing.
Yeah.
Okay. So, excellent.
And the important thing to remember is that the technology is scalable, so we can scale it up.
Very good. Hey, another question, is there any impact of the acoustic waves on the well integrity of old wells?
No. With the well that we're running in now, in this field is 50 odd. The field itself is 50 odd years old. We have seen improvements in injectivity in some of the other injection wells that are within that 3-kilometer diameter circle. There's about 3 or 4 other injection wells, and they've also seen some improvement in injectivity, which shows that you're basically moving that pressure pulse quite a ways out in the reservoir. So you're doing reservoir simulation, not wellbore stimulation. It's designed to work on the liquids. And so in terms of wellbore integrity issues, degradation of cement, degradation of casing, it's not an issue for us. This is it's a 40 hertz pulse. So it's not going to do, it's unlike ultrasonics, which are essentially wellbore specific, or some of the other technologies out there. This is designed to work over a long period of time, put energy into the reservoir over a long period of time.
Hey, and has the technology been trialed using other injection fluids like steam?
Steam, I don't think would work because, again, your steam is a compressible fluid. And so I think that would be a difficult challenge to run it with steam. We do have an upper temperature limit at the point right now of 100 degrees Celsius. So that would also cause an issue with steam. As far as CO2 EOR project, most CO2 EOR projects inject CO2 as a liquid. So you could use it in a CO2 EOR project. The device is made out of 2507 stainless steel, so it's highly corrosion resistant. So using it in a CO2 EOR project would not be an issue for the device.
And it's great to see some of these specific questions and what I suggest we do the moment we share the webinar with not just those that are in the audience today, but also others that registered and that are not here. Suggest we also include some of these operational parameters such that people can assess the applicability.
We're happy to share that with anyone who's interested. We can share that in detail with anyone who's interested. And we'll also be happy to look at individuals. If they have a reservoir they're thinking about running it, we're happy to do an assessment of it to see whether or not it's applicable. We won't run it if we don't think it's going to work. That's, our goal is to put something out there that we believe will work for an operator. It doesn't do us any good. It doesn't do the operator any good to run something that's not going to work.
Absolutely. You want to see more results like the one you had for the Permian, or the slide that you showed. It would be excellent. Let's see, one other question. What's the power consumption for the transmitter?
So the power consumption for the device directly is runs off of a permanent magnet motor that runs off about a 1/4 amp at 60 volts DC. So when you think about that, it's the current cost to operate the device in the U.S. is about $1 a month. Or in terms of what we've seen for improved recovery in the field that we're in, it's 1/10 of a cent per barrel. So very low cost to actually operate the device. What really puts the energy into the reservoir is the water that goes through it. Because remember, I said it's about 100 cubes a day is a minimum. We're currently running more than that through the device in Texas. But that's where your energy that gets applied to the reservoir over a long period of time is the water that we run through the device. Yeah. So it doesn't take much to spin it.
Excellent. There are a couple of other questions related to the operational parameters, but suggest we cover those later on if we have time left. But what's definitely good to do as well is, indeed, as discussed, to put it in a note. I mean, just to give one other example question, whether it's possible to run in sour environments. But let's park that one for the moment, and let's go to some of the commercial elements that are being asked here. What's your commercial model, your framework for the US And perhaps linked to that, say, how do you monitor for optimization during life of tools/deployment? Not sure whether I'm phrasing this correctly, but effectively, what's the commercial model for rolling this out?
Okay, so I'll let Kevin can do the commercial model, and then I can talk about tool life and how we monitor that.
Sure. In terms of commercial model, we're looking at two different models depending on the preference of the operator. So one is that we will, sell the tool, which is roughly a sort of $300,000 for the tool and the system itself. That includes the packer and the cable. It's the entire system, a control system at the surface. And then the cost to install is location specific, but we estimate that between $50,000 and $80,000 currently. So for something under $400,000, the entire unit gets installed. We're also willing to work with an operator and basically offer the equipment on a lease basis.
And it's worth noting that with the current production uplift that we've seen in Texas, that it's generating roughly $1 million a year in additional revenue to the operator. Based on sort of the $80 oil price plus or minus. So easily pays out in less than a year to run one of these things in the field.
And if we haven't made it clear yet, so the current pulse, we're going down an injection well, and that's impacting roughly a 2-mile diameter circle around that injection well. So we're hitting roughly 30 producers currently from one device being deployed, and that's it drives the economics.
Correct. And in terms of how do we monitor for tool life, so we get direct feedback from the device through our control panel system on the surface. We have two ways to communicate. We have a Iridium satellite connection that gives us a report once an hour, and then we also have Wi-Fi access so we can actually watch the thing run continuously. I would love to show that today, but they've had a storm that knocked the power out to the field this week, and so everything is down in the field, and we're just waiting for the power to come back on to get the device back up and running. So what we can do is we can monitor that current draw, and we know that the device is not working if the current draw goes below its sort of operating range of 0.15 to 0.25 amps. So if it drops down to, when it's not running, it's like 0.01 amps. So we'll know immediately if it's not running, and that's how we can determine whether or not the tool is operating. And our next generation design is that we're working to add some more communication where we can directly communicate downhole and actually calculate and determine and read what the current spin rate is on the device, so we know what specifically the pulse rate is that we're putting into the reservoir.
Hey, and a question linked to payback time is how quickly do you see results the moment you switch on the device? Is it fairly quickly, or how long is it roughly before you see tangible recovery results?
Is the question is response time?
Correct.
So in New York, the New York tests, I think we're probably in the 60 to 90 day range before we saw a response. The injection rates there were about the same to start with as what we did in Texas. In Texas, we saw a response within 30 days. And I think a lot of that had to do with the well depth. The field was pressurized already because it had been under water flood for a long period of time. Where in New York, we ran it in some fields that were essentially pressure depleted. So we had to build up some pressure and build up a little bit of a pressure differential to actually start to see the improvement in the production well. So I think the Texas deployment is much more representative of what you would see running in a conventional water flood, where we saw a response within 30 days.
Excellent. Hey, and what are your expansion plans? So there's plenty of scope in the US, but outside of the US, are you looking at specific parts of the world?
We have looked at some operations in the Middle East historically, but haven't sort of expanded beyond that. We've had a little bit of investigation into some of the mature fields in Indonesia, just looking at scoping possibilities. We had some inquiries, I believe, from Gabon, some companies that were there and have looked at, again, sort of a preliminary look. I think any place where you've got that fits those operational parameters would certainly be a candidate option outside of the United States. But we've been focused on U.S. and North America primarily for convenience for us to get to the field, but we would certainly look at elsewhere. We are working with Saskatchewan. We recently received preliminary approval from the government of Saskatchewan to get a royalty credit for installing this device in fields in Saskatchewan. And there's thousands of wells in Saskatchewan where this would be applicable and useful.
Yeah, excellent. So you covered a lot already, and we have time for a few more questions. There's actually still multiple questions we haven't addressed yet, but what we'll definitely do is to get the full list of questions to you. And it would be great if you can address
Absolutely.
those. But certainly one question, can you run multiple tools in a horizontal, for example, just to come back to some of the operational parameters?
I think that would be a challenge because, again, the current design is set up to where you have to run power to the device. So it would be difficult. It would be something you could probably work on the design where you could, because it doesn't draw, each device doesn't draw a lot of power, but you've got to figure out how am I going to get the cables sort of spaced out in between to run multiple tools in the horizontal well. What we were working with an operator in Colorado to run in the Denver-Julesburg Basin was to run a device in a vertical well that was completed in the same formation as the offset horizontal wells. And we were quite a ways down the road with that company, and then the company was sold to somebody else, and they sort of, they were focused on how do we integrate all these other companies because it ended up being another merger, so the project kind of fell by the wayside. But we have had some interest recently from another company that's expressed interest in doing a test, and that would be probably the direction we would take, is that let's look at either running it in an existing vertical well, because a lot of these fields have vertical wells that are completed in the horizontal zone, the DJ Basin, the Eagle Ford, and so that's what we would look at doing. And that way you're not taking one of your horizontal wells out of production. Because again, our goal is to not, sort of when you look at the risk analysis on this thing for a company, it's pretty low risk in terms of cost. And if you're not going to lose production by running it. If it doesn't work, you just don't get an increase in production. If it does work, you get an increase in production.
Are you looking for other trial candidates?
I'm sorry?
Are you looking for trial candidates?
Yes,
absolutely.
We are actively looking for trial candidates, and what we're currently talking to operators about is that we will wait until a production uplift is seen before we charge the operator. We're very confident once we've done our analysis that we're in a field where we believe this will work, that we're willing to do that, to put our device down hole and then wait to recover after we've seen the uplift.
Precisely.
Yeah. Excellent. So it's 1:30 the hour, and I suggest we end here. There's still many more questions, and actually, it's great to see the interest in this technology. It's very impressive, and we'll share the recording with everyone that registered, everyone that attended, and I think you indicated you're willing to share the slides as well.
You bet.
And yeah, it was a great overview, very impressive. So thanks for the presentation, Kevin and John, and for answering the questions. And I realize not all the questions were answered, but I think we could continue for quite a bit more time. But let's leave it here. And of course, anyone interested, you can follow up with Kevin and John directly. Thank you very much. Have a great rest of the day.
All right.
And once again, thanks, Kevin, John.
Great.
Right,
thank you, Eric.
Thank
everyone, for your time.
Good evening.